One of the main differences between electromagnetic waves and sound waves is electromagnetic waves are transverse. This is what you'd get if you tied one end of a rope to the wall and whipped the other end back and forth, up and down. Uh, the vibration is happening perpendicular to the direction the wave is traveling. So you could snap this rope tied to a wall and send a pulse down it away from you, but the wave would be moving back and forth as it traveled down. Sound waves, on the other hand, are longitudinal waves, and they oscillate in the direction they're going, kind of like if you slapped one end of a slinky. For the light waves, this back and forth oscillation happens, or for the sound waves, the back and forth oscillation happens in the direction the wave is traveling, but it's in perpendicular directions with electromagnetic waves. So here we've got wave traveling in the z direction, E field and B field oscillating again in directions perpendicular to each other. These waves have a wavelength, which here would be this. So this is showing about 1 3/4 wavelengths of this wave, because one wavelength is the full pattern of sine or cosine. So it's when the wave comes back to its original position going in the same direction. So for example, this point and this point have the same value of E field, but here it's getting bigger and over here it's getting smaller. So you have to wait. If you're going to look for a wavelength from here, you go through that point, through all these negative points, and then back up here. So this is one wavelength. And the same thing for B. If we wanted to talk about in time rather than in space, so we imagine we're frozen here at one point and this wave is coming across us, the time for this to move would be one period. And again, it's more common for us to talk about the frequency, which we use f for that, which is 1 over the period. We generally use f. We sometimes use this, which looks like a v, but it's not. It's the Greek letter nu for frequency. So you'll see that about equally with f in most physics books. You can see either one. If we multiply the frequency and the wavelength, we get the speed of a wave. You can think of this as if you're watching a train go by. If you know the size of the cars and you know how many cars per minute are passing you, you could multiply those two things together and get the speed of the train in, feet per minute or whatever. Ordinarily, we'd use a v for velocity of light, but for light we use c, just traditionally. And when I talk about light in almost every case, what I really mean is all forms of electromagnetic radiation, and we'll look at the whole spectrum lower. We've seen this value before, the speed of light. This is for a vacuum, lambda times f equals c. So we know how fast it goes. We know the wavelength, we know the frequency. We can also look at the energy density. Is there a difference between a radio wave and a laser? And you could probably guess, yes, there is. Energy density means how many joules in a cubic meter of this field intensity. There's a contribution from both the electric and magnetic parts. So we could write it like this: 1/2 epsilon naught E squared for the electric part, B squared over 2 mu naught for the magnetic part. Or we could use E equals CB and write it either as epsilon naught E squared or B squared over mu naught. The intensity is another thing that we'll look at, and that's defined as power divided by area. What that means is the intensity of a point source of light drops off as 1 over r squared. So we can write the intensity as P over A, like that, and generally light spreads out in all directions evenly. If we look at what's called a point source, it looks a little bit like, if you've ever seen a picture of a atomic bomb detonation, the way you get this expanding sphere. That's what it would look like if we could watch light expand when we turned on a light. The area here is the area of the sphere, which is 4 pi r squared, and r is the radius. In general, if you're talking about intensity where you are, r is the distance between the source and you. So we can write I is P over 4 pi r squared. If we want, we can write it in these forms, the intensity in terms of the fields. It's not quite as useful to us in this class. An example of the way this intensity drops off with distance, we can look at our solar system. For space probes that are going to be near the Earth, satellites that orbit the Earth, that kind of thing, a lot of times they're powered by solar cells. And we might think that would be a good idea everywhere in the solar system, but it turns out it's not. Going to visit Saturn, for example, it's almost 10 times as far from the sun as the Earth is. So the solar intensity of the Earth, which is 1400 watts per square meter, that's going to drop by almost 10 squared, almost a factor of 100. So at Saturn's distance, the sunlight intensity is only 15 watts per meter squared. This is why the space probe that went to Saturn most recently had to have a nuclear battery to power it, because there's just not enough sunlight out there. In general, when you double your distance to the source, the intensity is going to drop to 1/4 of what it was. Triple the distance, it's down to 1/9. 4 times the distance, 1/16, etc. This is the reason why people who work in nuclear medicine clinics and hospitals are told to hold the radioactive samples that they're taking to inject into a patient at arm's length rather than hold it up against their body. The further away from you it is, the smaller dose you get. Now, knowing all that, we can look at a few different parts of the electromagnetic spectrum. For example, the wall outlets actually radiate like radio waves at 60 hertz. These are incredibly long wavelength, though, 5,000 kilometers. So they don't have any, this radiation doesn't have any major effect on our lives unless you're trying to measure something and you keep picking this field up. But in general, this probably won't affect you much. AM radio, the frequency can be read off of your radio dial. It's 530 kilohertz to 1700 kilohertz, which means wavelengths in the hundreds of meters. If you've ever been out west and seen really tall radio towers, they're probably AM radio, because the optimum size for a radio tower is usually 1/4 of a wavelength. So here we'd be looking at something like 150 meters or about 500 feet. FM radio is much shorter wavelength. It's from 88 megahertz to 108 megahertz, and it's about 3 meters. By the way, these are not physical specifications, this AM and FM. This is what the FCC says in the United States we're going to use for AM and FM radio. Broadcast TV goes from 54 megahertz to 700 megahertz. Very long ago, before the signals switched to digital, you used to be able to pick up channel 6 broadcast TV on an FM radio, because there is some overlap here. Cell phones, Wi-Fi, microwave oven, all those things are in the few gigahertz range, which means their wavelengths are centimeters or several centimeters. Terahertz scanners, which are in use at some airports and can see through your clothes, their frequencies range from 300 gigahertz to about 3 terahertz. So the wavelengths are a millimeter to about 1/10 of a millimeter. This 100 micrometers, that's about the thickness of a hair, more or less. Infrared, that's like your TV remote. That's what night vision goggles see. That's what thermal cameras are looking at. That's in the 3 to 300 terahertz region, and the wavelengths are 1 to 100 micrometers. Visible light is 400 terahertz to 800 terahertz, and wavelengths are 380, that's like blue, 380 nanometers up to 760 nanometers, that would be red. Ultraviolet is beyond 380, so smaller than 380, down to about 10 nanometers. So from 800 terahertz to maybe 3 times 10 to the 16 terahertz. This is where you start to get into damaging radiation. You know, ultraviolet rays can give you skin cancer. It'll fade the paint on your car. It'll fade fabric, all sorts of things. X-rays typically range from a few nanometers down to 10 to the negative 11 meters. That's like 1% of a nanometer. That's 10 to the 17th to 10 to the 19th hertz. Above that frequency, or below this wavelength, we're talking about gamma rays, which are nuclear decay byproducts.